Yeah. So, yeah. So just a quick note. Yeah, I'm Rahul Anantharaman. As I said, I'm from Center of Energy Research, and for the 1 hour today, it is a very broad topic that we have. So I'm going to start off by presenting my organization to you. I'm not sure if you know that. So just a very quick presentation of the organization where I work at. And then start with where do the CO2 emissions we are talking about come from? What is the role of CCUS in a net zero scenario? I'm taking the idea of clean energy to mean a net zero scenario. That is, we don't emit any net CO2 as a society, which the energy system is a very big part of it, but it is not limited to the energy system itself. Then talk a little bit about CO2 capture, and give an example of that in hydrogen production, the role of CCS in hydrogen production and the future energy system scenario. What is the role of CO2 utilization, carbon dioxide removal technologies, and with a specific mention on waste to energy with CCS, and summarize the talk. So when I'm going through this, like I mentioned, it's a broad topic, so I've gone very high level with it. So I'm not going into details. So please don't hesitate to stop me to ask me any information you want. Even halfway through the talk is fine. You could either raise your hands, or better yet, you could interrupt me and ask me. That should be fine. It is not talk I need to give a certain way. So please let me know in case you have any questions or you want any more information, details as I'm going through this stuff. Okay. So Center of Energy Research, we have a tagline that says we shape the future energy solutions. And we are CINTEF itself is a large research organization. So we are over 2,000 employees. It is one of the largest in Europe and the largest in Scandinavia. We have people from over 75 nationalities. I myself, I'm an Indian working here in Norway. So we have over 3,700 customers with really large revenue. So we are a non-profit organization. So we do project-based research, but are non-profit organization. And what we work on, I tend to say we work on everything except nuclear power. So we work on a large number of areas, out of which the topic I'm going to talk about today is the one that my department and group works on specifically. So Center of Energy Research is an institute for applied research dedicated to creating innovative energy solutions. And the areas that Center of Energy Research works on is energy efficiency, carbon capture and storage, which I'm going to talk on today, hydropower, offshore wind, bioenergy, transmission, smart grids, hydrogen, offshore energy systems, which is very important here in Norway, and also zero emission transport, which is an important topic that is starting to build up here. Okay, so I move on to the first topic part of the presentation. So where does the CO2 that we're talking about come from? Where is this problem coming from? This is a slide that looks at the elements in the Earth's crust. So this is only the Earth's crust. And if you look at the rock forming materials, you see that you have carbon as one of the materials that tends to form rock. And an example of this is calcium carbonate, which is also all the three elements are basically here. If I use so you have CaO and C, so calcium carbonate. This is used in cement production, which is limestone. It is calcined to lime, and there is CO2 emissions from that in cement production. So this is not fuel, but this is just when we are extracting or using rocks from the Earth's crust in our chemical processes, either to make cement or other things, we are going to emit CO2, most likely, because there is carbon as part of that. But of course, that is not the major one. Where majority of the CO2 is the use of fuels. And fuels tend to have carbon in them, except hydrogen. Most other fuels or all other fuels have carbon in them, and burning them emits CO2. And that is where most of the CO2 that we use comes from, is burning of fuels for energy, either in industry or other residential purposes, or for transportation, etc. And that's where the CO2 comes from. This is a really nice figure I like to use that shows where the CO2 is coming from, or where the greenhouse gas emissions are coming from. And we shouldn't limit ourselves to CO2, because methane is a very bad greenhouse gas. It is 28 times the effect of CO2. So it's so 1 kilogram of methane is 28 times equivalent to 28 times CO2. So we need to look at the whole picture, and this kind of tells you what is the source of all these CO2 emissions that we are seeing in the world today. There is an updated figure also for 2018 at this website that you can see at the bottom here. And this gives a good understanding as if we want to tackle the CO2 issue or the greenhouse gas issue, where should we focus on? Another version of the same data, but only in terms of CO2. So the methane and nitrous oxide are converted in terms of equivalent CO2. And that data converted here shows that energy is the source of 73.2% of our CO2 emissions. And a significant part of it is the energy used in the industry. And then, of course, we have transport and energy use in buildings. The industrial emissions that we talk about, like I said, for cement is approximately only 3%, even though there is also a fuel use in the cement industry, which comes as part of this here. So, to summarize, we could say that CO2 emissions from energy use is primarily from the carbon in the fuel. And there is also other amounts of CO2 emissions as a byproduct of chemical reactions needed in the production process. Example, the most simple example is clinker production, but both ferrous and non-ferrous metal productions use carbon as a reducing agent. And when you use carbon as a reducing agent, to produce the metal, you end up releasing the carbon as CO2. And that is a source of a lot of CO2 emissions, particularly in iron and steel. And here in Norway, we have a lot of non-ferrous metal production like manganese and silica. And there is a lot of CO2, and also aluminum, actually. There is a lot of CO2 emissions that are associated with that because of the use of carbon as a reducing agent. And of course, there is the case of hydrogen, ammonia, or methanol, where you convert your natural gas to hydrogen and CO2, and then separate out the CO2. So these are all the sources of CO2, which is not directly using a fuel from a fuel, but through production processes for metals and other items that we use every day. So I'll directly jump into the topic and then so I'll present what is the role of CCUS in a net zero scenario, and then talk a little bit more about the details, because the idea is to present what it means first. So there have been many studies, many studies looking at energy systems. So you do energy systems modeling, either regional, country-wise, region-wise, or even continent-wise. We do quite a lot of studies in Europe. And these models, the output from the models depend quite a bit on the inputs you provide to it, as with everything. But the problem is these are so, how should I say, high-level models that you tend to provide very simplified assumptions to these things. And there are a lot of biases when you do these modeling, depending on who's doing the modeling. So an example is, if you go to the website shown here, they have a collection of 56 peer-reviewed papers, which tend to show that you can have a clean energy system, which is 100% renewables. Now, is that possible theoretically? Yes, it is. Is it possible practically? Probably not. And I should say, certainly not. And why is that? You have things like you would need the model predicts crazy amounts of energy storage, batteries, and you probably won't have enough cobalt to supply all the metal you need for the batteries, things like this, material issues, and without considering proper constraints, without putting in physical constraints on the system, you can design anything you want to have. So there are these papers that show that everything can be 100% renewable, so the whole, nearly everything we see around us will be electrically driven. So there is no need for any other fuels but electricity in our world. And I would say when you see such studies, always handle it with care. There are a lot of assumptions that we need to dig into, and that is the idea of what I'm trying to present today, is to give you the basic information that you can use to try to understand the studies that come out of these different institutes around the world. So compared to the studies that you saw there, I'll talk about two studies here which show that CCS or CCUS has a role to play in the future energy system scenario, particularly to get to a net zero. When I say a net zero emissions, what I mean is you are not emitting any CO2. So whatever's overall, whatever CO2 you're emitting, you're either capturing or putting it down, or you're using fuel sources or energy sources that don't emit the CO2. So in these two work, one of them is some, like the Hydrogen for Europe report is something that we worked on at Sintef Energy. And of course, IEA have presented the Energy Technology Perspectives 2020, which had a special report on carbon capture, utilization, and storage. And there you see that CCS contributes to the decarbonation of the power sector, because there will still be some coal-fired power plants, some natural gas-fired power plants, biomass plants. So you need to capture the CO2 from it to get to net zero. CCS needs to be used in the decarbonization of industry. It's like the cement case I talked about, or hydrogen, or steel, for instance. And also it enables low emission hydrogen production for natural gas. I'll talk a little bit more about hydrogen a bit later. And also CCS enables carbon dioxide removal technologies, and we'll go through what these are a little bit later. I don't see I have any questions so far. Please let me know in case you have any questions and want to ask me to stop. So according to the IEA, I'll focus on the IEA report because it is a much more renowned organization and everyone knows about it and tend to follow what they say. So according to the IEA report, CCUS has a significant role to play, as you can see in the cumulative amount of CO2 emissions that are reduced by CCUS. And most of this, you see, comes from capture from coal, which they see increasing in 2050 and then reducing by 2070, but also natural gas. And this increase in natural gas is both power plants and natural gas as conversion to hydrogen. And there is significant biomass that is being captured from biomass combustion. And again, most of this is biomass combustion to produce electricity. Initially, by the year 2050, there will be a lot more CO2 captured from industry according to their analysis, after which time they see it being electrified, so less CO2 emissions from fuels from the industry, so less capture required from the industry. But then you have a little bit starting in 2050, but quite a bit of it in 2070. You capture CO2 directly from the air, or you remove CO2 from the air. And that, again, I'll talk a little bit about that later again in this talk. So we've seen that CCUS has a role to play. So let me give you a very quick overview of CCS, or what is CCS. So basically CCS is the fact that you have CO2 in a source and what you're trying to do is to remove the CO2 from the source. So you're capturing that CO2. When you use fuels, the CO2 comes from burning the fuels. So in the case of power plants or combustion processes, there are three main routes to capture your CO2. The first most common route is called post-combustion or end-of-pipe capture, where you have your fuel combustion or chemical process conversion, as the case may be, and you get a stream primarily of CO2 and nitrogen, which you then separate out. And this CO2 then goes to a CO2 compression or liquefaction, depending on the transport that you're using, and then goes to storage or utilization. And the main separation here is between nitrogen and carbon dioxide. And the most mature technology is absorption using amine-based solvents, and this is applicable to both new and existing plants. And this is the most common form of CO2 capture that we talk about. So typically industry uses this, power plants tend to use this. So this is the most common form. When we say CO2 capture, this is what we think of. Another route is the oxy-fuel combustion. Here, what you do is rather than burning the CO2 in air, which is where the nitrogen comes from, what you do is you burn it in oxygen so that you get rid of the nitrogen. And then theoretically, you will only have CO2 and water as a product from your combustion, because the C and H in the fuel will combine to form CO2 and H2O. So then it is easy to separate out, just condense out the water and you get the CO2 in theory. But that is not the case. So the process is a bit more complicated. Why? Firstly, burning something in pure oxygen is very difficult. It results in very high temperature. So what you need to do is you need to recycle some of your CO2, or quite a lot of your CO2, in fact, back to as a sort of a temperature control. To reduce NOx formation, etc. And also you don't get 100% pure oxygen. So what you end up having is a little bit of nitrogen, a little bit of argon, etc. in this gas, which you then need to separate out, which is typically done by CO2 liquefaction. Another reason why it's not just condensing out the water is that there can be air leaks into the system. This is not pressurized, so this is usually at atmospheric conditions or slightly below. So what that means is that there are chances for air ingress into the system. The main separation that happens here is the air separation unit, and this is a well-established unit where cryogenic air separation is used to for large volumes oxygen supply. And this is a well-established technology, highly efficient process. So this separation exists today. There is a little bit of separation that goes on here in the green box in the CO2 compression and purification, but that is a very small part compared to the energy required for the air separation part. The last route that we can talk about is the pre-combustion. And as the name suggests, what we are doing is we are capturing the CO2 before you combust it. And how do we do that? Either the fuel, either natural gas or coal or whatever the fuel is, you have biomass. You can either gasify it or reform it and convert it to syngas, which is CO, which is a combination of CO, CO2, and hydrogen. And to ensure you separate all of the CO2, you go through a water gas shift, where some of the, or most of the CO is then converted to CO2, and you end up having mainly CO2 and hydrogen. And here you capture the CO2, and then you burn the hydrogen, either in a furnace or whatever the application is, even in a gas turbine. And so this is where, so you are actually capturing the CO2 before the combustion process. So it's called pre-combustion. So here the main separation happens here in the or between CO2 and H2. There is also the air separation that takes place, but it's not. It's a small part compared to the larger part, which is the CO2 hydrogen separation. Actually, a fact is that most of the energy in this process, or energy penalty in the process, is not in the CO2 capture or compression. It is in the conversion of the fuel to hydrogen. This is where you lose most of the exergy or the energy content of the fuel. And that is where a lot of research is now focused on having a more efficient process to convert to hydrogen. The CO2 capture part is not that significant in the end. So we've been talking about these separation techniques. So what do we use for CO2 separation? The most common one is absorption-based separation. So it can either be adsorption with a B as in boy, or adsorption as a D as in dad. So in the case of absorption, what you have is you have a liquid that flows typically countercurrent to your gas containing your CO2 that you want to remove. They are contacted with each other in a unit, and CO2 is captured. And this solvent which captures the CO2, which is your absorbent here with a B, it then goes to a regeneration unit. And the regeneration unit is where you supply energy, and the energy is supplied so that you separate your CO2 from your solvent. And then the solvent is regenerated, CO2 separated, and you send your solvent back. And this is an absorption process. In the case of adsorption with a D, as in dad, here what you do is you have solid particles rather than liquid. And they typically are surface phenomenon here. Little bit of, it's not only physical adsorption, but sometimes it's also chemical adsorption, but it can be either of them, but it follows similar. So you send them to a unit where the CO2 is adsorbed on the solid sorbent. It is then regenerated using energy, either as the form of heat or in the form of electricity. If you use something called pressure swing, where you change the pressure between the capture part and the regeneration part, and that means you need to supply electricity in compression or in vacuum, depending on what you do. So that is sorption-based technologies. And they are the most commonly used technologies for CO2 capture, or the most widely studied ones. The next one, which is quite widely looked at, is our membranes. And the principle of a membrane is very simple. Basically, you have a membrane or a material which allows one component to go through preferentially over the other components. Say, for instance, you have CO2 nitrogen, it allows CO2 to go through rather than nitrogen. So that way, more CO2 is concentrated here, and you separate the CO2 from the nitrogen. And it works on partial pressure difference, or a combination of the pressure of the gas here and the pressure of the gas here, the difference between the pressures and the CO2 concentration. And so you need, was there a question or something? Okay. So you need to supply some power to either compress the gas or to have vacuum on the permeate side, which is gas B. The other technique that can be used is phase change. And here, what you're doing is you're either going from most of them, so you have CO2 in a gas phase. So you either liquefy the CO2 by compressing it and cooling it to really low temperatures, or you solidify it directly in a process called from gas to solid phase directly. And here you have to supply even more power and even more cooling refrigerants to get to even lower temperatures so that you directly solidify your CO2. So that is the phase change. So an advantage of phase change is you don't use any chemicals at all. You don't use any chemicals in membranes also directly. And they are not used much, but there are membranes, there are chemicals used in making these membranes that on an overall life cycle perspective could be harmful to the environment. Whereas when you think of phase change, you're not using any chemicals at all. And another very interesting option for CO2 capture, and this is only for the case of combustion, less for industrial capture, but for combustion processes, what you can do is you can do something called chemical looping combustion. And what you're doing here is you are taking what is called an oxygen carrier, which is a metal oxide, basically, which is oxidized in an air reactor when you pass air through it. And what this does, this metal then takes up oxygen, which becomes the oxidized metal, and it goes to the fuel reactor where the fuel is burnt. And the oxygen in this metal actually reacts with the fuel to reduce the metal that is then sent back, and here you burn, and there is mainly CO2 and water that is released. And you actually produce energy here because you're doing combustion. So this is a very efficient process for separating the CO2. You can say that it inherently separates the CO2 in the way you do it. However, it is a very complicated from a practical perspective. Theoretically, it is really hits the sweet spot, but from a practical perspective, it is a very difficult process. So I'm giving you an overview. I could spend, I've taught courses on these capture technologies for a couple of days, so we won't go into the details here, but in case you want to know anything in detail about these capture technologies, please do let me know. So I talked about the different capture technologies, but they are at different stages of development. And this figures from a publication from 2018 shows where we are with the different capture technologies. So you see that absorption can be low depending on the kind of solvent. If amines are the most advanced solvent, and so they are at a very high TRL or commercially available, whereas ionic liquids and things of that sort are not. So they are the next generation of solvents that are coming up. Similarly, membranes, different types of membranes exist for different requirements. So they are at different TRLs or technology readiness level. We are not going to talk too much about transport and storage, but transport in pipelines and ships are technologically available, so you can do it. It is being done today. The only problem is the logistics of it, which is the biggest headache. How do you design such a system to do it over time as you capture CO2 over time? Okay, so this gives you an overview of the technologies and the storage potential also. So how will you select a capture technology? Of course, it depends on the CO2 partial pressure. And what do I mean by CO2 partial pressure? It is a multiplication or a combination of the CO2 concentration in the flue gas and the pressure at which it is available at. So for instance, cement industry has approximately 20% CO2 and it is available at 1 bar. So the partial pressure is 0.2 bar, because 20%, 0.2 multiplied by 1 which is 0.2. In the case of NGCC, not NGCC, I'm sorry, hydrogen production from natural gas, you have it at, say, 20 bar. The syngas is at 20 bar, and you have approximately 30-40% CO2. So what it is? So it's 0.5, 0.4 times 20, right? So it's 8. So there are these large differences in the partial pressure. So higher the partial pressure, easier it is to separate. Higher the partial pressure, you use option which are pressure based to separate the technology, or even liquefaction, for instance. So at lower partial pressures, you would use absorption or temperature swinger, because it has to react to separate rather than use the pressure as a driving force to separate them. Another important aspect is what are the impurities in the CO2 stream, and how will it affect either the adsorbent or absorbent in separating them, or even the membrane. Are there any physical or material limitations that are available? Can you integrate it with the plant? So when I talked about absorbents, I said you need to supply energy to regenerate the solvent. And that energy is typically steam at 120 degrees. So I keep talking about cement because it's a very easy plant to talk about, and it's nearly everyone knows about a cement plant. It's so widely available and seen everywhere. So in the case of a cement plant, there is not much heat available. So in a power plant, you have steam available, but in a cement plant, you don't have steam available. So how will you regenerate the solvent? You will need to burn fuel to generate steam and then regenerate the solvent. So it's not very well suited to cement, even though it is to a certain degree. There are some ways around it, but it is not the easy. Not only the capture process, process, or the process producing the CO2, and what else is available outside that we can interact with. Another important choice is the maturity of the capture technology itself, the complexity of the process, flexibility. If it's like a natural gas combined cycle that you would use, which is load following, then it'll go up and down. Then this is where you have this. You need to have flexibility in the capture technology. Also, this is a big point now in that, for instance, solvents tend to degrade in the presence of oxygen at high temperatures, and they release carcinogenic substances in the air and in the water, and that can be an issue. So toxicity of the chemicals in the process is an important aspect to also consider. So there are a lot of these things to consider when you do it, and typically organizations like us at Syntef, we do these kind of benchmarking studies that compare different technologies to help end users select the most suitable capture technology for their application. So this is a little bit of an overview of the different CO2 capture conditions that are available, or you can see. So this is the partial pressure difference that I was talking about. So the syngas from natural gas reforming, because it has high pressure and 30-40% CO2, you have high, it is very different here. Coal has much higher CO2 concentration, and also it usually operates at 40 bar rather than 20 bar that reforming operates. So the partial pressure of CO2 is also very high there. Similarly, steel production is slightly pressurized. It depends on the production method, but it is slightly pressurized, so then you can have and it is available at high CO2 concentration. So you can see where it is on this figure. But as regards the other, most of the other emission sources, they are all atmospheric, most of them. Aluminium production has really low CO2 concentration because the CO2 comes from an electrolytic process where Al2O3 or bauxite is basically reduced to aluminium, and they use carbon anode here, and this process generates so much heat that they use air to drive out the CO2 and cool it. And so the CO2 is diluted by air, so it's approximately 1% CO2 at atmospheric conditions. So it is very difficult to capture that CO2. And then you have natural gas turbines, the NGCC power plants, which are around 3.5 to 4%. Flue gases from refineries, typically between 8 to 14, 15%. Coal-fired power plants, also in the range 10 to 15%. Cement has a wide range, 20 to 30% CO2, depending on the process and the raw material that we use. And then the oxy-fuel part that we talked about earlier, because you burn it primarily in oxygen, it has a very high CO2 concentration compared to the other cases here. So this gives you an idea of the different capture conditions that you would see typically in different plants that are available today. Now, when you talk about CO2 separation, this doesn't come for free. Nothing in life comes for free, right? And when we look at separating the CO2, we need to supply energy for any kind of separation process, or any kind of conversion process. Typically, you need to supply energy that needs to separate the CO2 from the nitrogen or whatever you are. So to give an understanding as to what it means to capture CO2 or how much energy you would need to capture CO2, you could use this thermodynamic property called minimum energy, which is, I won't go into the details here, but it is something that can be calculated based on thermodynamics or physics. There is a strong foundation for this, and you can calculate what is the absolute minimum energy that I need. So this will not be what you will do practically. This will be like in the best case possible, like without breaking the laws of physics, what is the best I can do? Of course, all the practical limits come then, so then capturing it will require more energy than not. To be very, very optimistic, you can assume that you are double the amount presented here compared to what is here. So on the x-axis, you have the CO2 concentration, that is the concentration in the flue gas, if you will, that you want to capture your CO2 from. And this is the specific energy required for separation. As you see that as the CO2 concentration decreases, the energy requirement doesn't increase linearly, it increases exponentially. And it goes up and shoots up pretty nasty beyond a certain point. And as a frame of reference, just put up these typical flue gases that you're looking at. Capturing from a cement plant, say it takes around 200. So this is the absolute minimum, right? 200 kilojoules per kilogram of CO2. But if you go to a natural gas combined cycle power plant, which is approximately 4.5% CO2, you're nearly doubling the energy required to capture 1 kilogram of CO2 from these two conditions. And going from a cement plant to an aluminum plant, you're nearly tripling the amount of CO2, so the amount of energy, nearly tripling amount of energy that you would need to capture 1 kilogram of CO2. So where you capture your CO2 is important, and how you capture your CO2 is important. So you could say that if you want to reduce emissions from a country perspective, low-hanging fruits are easier to capture. Things like cement, um, steel, hydrogen. These are cases, and again, going back to this figure. So the further away you are on the right, the easier it is to capture the CO2. So that's what you want to do, is you want to capture as much of it from either further away on this side or further away on this side. So being closer to the 0 point makes it worse to capture CO2. So try to get away from it as far as possible. Of course, there is no getting away from it, that we need to still capture CO2 from a natural gas combined cycle power plant. So we need to still develop technologies there. But must keep in mind that this is going to be way more expensive. And and here is the CO2 accounting, that again, if you say that you don't capture your CO2, you actually emit quite a lot more of your CO2 than you actually, or when you capture your CO2, you use extra energy, and so that means there is some extra CO2 that's being emitted. So you, even though you capture 90%, your avoided is not 90%, you avoid less than the 90%. I noticed that I have talked quite a bit and I'm way behind on my schedule. So what I'll do is I'll skip through the hydrogen as a clean energy vector. Suffice to say that hydrogen is very important in the future as we see it. As the world is seeing it now, we are going through a hydrogen boom. Everyone is talking about hydrogen. And hydrogen from natural gas with CCS is the best way to provide hydrogen as we know it today. And even the cost seems to show that that is the best way forward. So there is also the topic of CO2 utilization, because the topic said CCUS. We don't ourselves work quite a bit in utilization. We focus primarily on capture and storage because that's the best way to get rid of the CO2. But there is a value for utilization, a small value. And there are three different routes to do this. Overall, first is mineral carbonization, where the CO2 can be reacted with minerals or waste streams. So it can be rocks, mineral rocks, or waste such as iron slag, or even waste to energy plants have fly ash that can be used to actually react with the CO2 to form carbonates. And this carbonates can be used in the construction industry and for long-term storage. So there is a value for it. It doesn't pay much, but it is very easy to do, low energy requirement. Next in energy requirement is conversion. So this goes along with this whole cycle also with this thing with circular economy, where you capture your CO2 and then you convert it back into useful chemicals, like polymers that are used in a wide variety of industry. And the thing is, the idea is that you're now replacing fossil carbon and rather using carbon that you have captured instead. But the energy requirement depends on the process pathway and this particular chemical that you're looking to convert to. The most energy intensive of these is fuel production. And there have been lots of talk about capturing CO2 from the air and also producing hydrogen from renewables, combining these to produce fuels, either methane again or methanol, etc., etc. But this is not a viable option unless you get really low CO2, hydrogen, and energy. Basically, most of these cases assume free energy and very cheap CO2 and hydrogen, which is typically not the case. So we've done a study, again, back to cement. We've done a study for the cement case a few years ago as part of a project that we were leading. And one thing is very clear, and this is something that has come up again and again by everyone who does these studies, that it must be important what you look as are you must look at it from the overall lifetime part of it. Only a small fraction of it can actually be used because the market is so small. So you can only use a small fraction of your emissions in utilization. But this small fraction that is used can help to provide income for the company in a sense to do the capture. But you must do a full LC analysis to evaluate the actual amount of CO2 that you store or is removed from the environment, in this case. Yeah, and these are a list of things to consider when you look at utilization. I'll very quickly touch on the role of CO2 removal, carbon dioxide removal technologies, and these are the cases where, so the world, or we want to get to a carbon neutral world or no net emissions. And this green area indicates all the other conventional technologies that we're using, renewable CO2 capture, et cetera, and we can get down the emissions to a certain amount. But there will still be emissions from other sources like cars or some kind of vehicles, transport, and this are very difficult to abate emissions which we cannot capture the CO2 from. So what do we need to do there? What we need to do is to then remove CO2 from the atmosphere, and that way what we can do is to offset the emissions that we are having in these cases that we cannot remove the CO2 from. So CCS has a very important role to play there. For instance, you can see here, there are these different options to capture, remove CO2 from the air, and you see that the permanence, or the longer that you're storing, goes down this way here, and the capturing either from biomass of forests, when you burn the CO2 wood and you capture the CO2 and either mineralize it or store it underground, then you get rid of CO2 from the air because the plants are taking the CO2 from the air, you're burning it, and you're using the energy and then capturing the CO2. Or you can use what is called direct air capture. There is 400 ppm of CO2 in the air, and people have been looking at capturing the CO2 directly from the air. This is very, very, very expensive, and like I showed the curve, the lower the concentration, the more energy it takes to capture the CO2. So this is going to be very expensive, but it is a process that we may need eventually because we don't capture enough CO2 with the existing processes today. And this just gives an overview of the costs of doing the different, and you see that CCS is an important tool here to remove CO2 from the air and achieve net zero and a clean energy system. So whatever we do, whether it is for utilization, storage, or capture from the air, we need to do a systems level perspective, an LCA analysis, to make sure that you account for CO2 the right way. And all CO2 is accounted for, the energy required in conversion and things of that sort. Everything is accounted for to make sure that you do remove net CO2 from the environment. So I'll very briefly talk about an important point, which particularly in the countries that you're all representing, is the role of waste to energy plants with CCS. So we know that what is CCS? Basically, you have fossil fuels, you burn it, either in industrial process or whatever, you have a product, but then you have CO2 emissions, which you then capture most of it and you put it underground, or utilize it if you want, but there is some emitted to the atmosphere. BECCS that I talked about earlier, which is bioenergy with CCS. What do you do there? As I said, you have trees which take the CO2 from the air and then you burn it or do biomass conversion either to electricity or biofuels. When you do this, you use biofuels, you release CO2 to the atmosphere, unfortunately, but there are other CO2 emissions from the conversion process, which is captured and stored. So here you are going from CO2 from the air to CO2 storage. So you're net removing CO2 from the air. However, with anything related to bioenergy, there are land use issues and there are limits to its sustainability. So this is where municipal solid waste comes in. So municipal solid waste is basically you have plant-based products as part of your municipal solid waste like food, but also products from fossil fuels. Now, what is happening in many of the countries is that quite a lot of it goes to landfill, where you have methane emissions. Like I said, methane is 28 times more potent greenhouse gas than CO2. So 1 kilogram of methane is equivalent to 28 kilograms of CO2. So mainly in landfills, you're emitting a lot of methane. So what is a better way to do this? A better way to deal with it is to take the municipal solid waste, which contains approximately 50 to 60% bio-based products. So then you capture you burn it or you incinerate it, you generate heat and electricity, you have the CO2 emissions which you capture and store it, and 1 ton of waste approximately gives 1 ton of CO2, which you capture 95%, then it's a very small amount of CO2 that you're emitting. And here you are then eventually removing CO2 from air. And there are no land issues. The waste is keeping on increasing. So what we're trying to do is to capture the waste as much as possible. And by doing this, you're doing 3 services. One is you are disposing waste in an environmentally friendly manner. You're reducing CO2 equivalent by 95%. You're supplying clean energy to the local energy grid. And it enables negative emissions to reach net zero targets. Typically in cities where most of the waste is emitted, where you have cars where you don't capture your CO2, you can capture CO2 from waste to energy plants. So to summarize, yes, so CCS has a role to play, utilization a much smaller role, but CO2 capture and storage is a very important part of it. And what kind of role? It avoids to lock in emissions from existing fossil power plants. You can retrofit them with CO2 capture. You can get net negative by using BECCS or bioenergy with CCS. And you can, in natural gas or in renewable energy systems with a lot of fluctuations in solar and wind power, you can use NGCC, natural gas combined cycle with CO2 capture to do that. So by doing that, CCS has an important role to play, and I've given you a brief. I'm sorry for rushing through the last part of my presentation, but hopefully you'll be able to take some understanding of the system as such. I don't know if there are time for any questions or if anyone has any questions, so please feel free. It is relatively quiet here.
Thank you, sir, for your informative and insightful talk on the carbon utilization and capturing techniques. And I believe all the participants will be taking this learning into their respective fields. And we truly appreciate your time here with us today, sir. Thank you so much, sir. If there is question, then we will get back to you and provide the answer to the participants. Thank you so much, sir.
Thank you very much. Take care then.